Hello, I'm an old guy and I do maths. Today we're going to look at remainder theorem and factor theorem. These are very simple ideas, but they have the ability to perplex and confuse. And I think that may just be the way in which they're stated. So, for example, I'm going to read to you from a textbook about what remainder theorem says. If p of x is divided by x plus a, then the remainder will be p negative a. What exactly does that mean, and how does it help? Factor theorem then states if p of a equals 0, then x minus a is a factor of p of x. That's a little more helpful and a little more understandable. In practice, what does remainder theorem do for us? Well, it's fundamentally a shortcut. It avoids having to divide a polynomial to discover its remainder. That's the practical use of it, especially for high school kids. This is what you want to know. So what I've done is I've taken a quadratic rather than a cubic or something more awkward, and I've divided it by a linear expression. And I'll just talk my way through this quickly. What you need to note is that there is a remainder and it's 40. That's the important thing. So we've got 2x squared minus 5x plus 7 divided by x plus 3. Multiply x plus 3 by 2x and we get 2x squared plus 6x, and we subtract that to get rid of this expression here. We're left with 11x plus 7. We multiply negative 11x plus 7, sorry. We multiply x plus 3 by negative 11 to get rid of this, and after we do our subtraction we're left with 40. The remainder, when we divide this by this, is 40. Now, imagine for instance that you have a cubic or a quartic and you're asked to do the long division of that. That's quite a bit of work. Now, remainder theorem allows you a little shortcut, and here it is. Okay, so if we take negative 3, so if we say that the value of x is negative 3, which means that the factor that we got it from was this, and you will note that this is the same as that. So what we're doing is we're just taking another form of this, which is the solution to this being 0, negative 3. If we take negative 3 and we replace x with negative 3 in this expression, what do we get? Well, this is what we get. We get 2 times negative 3 to the power of 2 minus 5 times negative 3, that's the x, plus 7, which gives us 18 plus 15 plus 7, which equals 40. Where have you seen this before? Up here. So, if you are asked, if you divide 2x squared minus 5x plus 7 by x plus 3, what is the remainder, or is there a remainder? You can do this rather than this. And as I said, once it gets up into the higher degrees, like x to the 4, x to the 5, it's much more streamlined to do this. Okay, so where do we go from here? Well, let's take a look at a slightly larger example, and this is of degree 3, so this is a cubic, and what we're going to do is we're going to try a factor. We're going to see if x minus 1 is a factor of this. Now we could do that by dividing this thing by this thing. But we're not going to do that. So what we're going to do is we're going to put 1, which is the value of x if this equals 0, into this. So let's go. 3 times 1 cubed plus 7 times 1 squared plus 3 minus 4. What does that come to? Well, it comes to 3 plus 7 plus 3 minus 4, which I think is 9. I hope it's 9. I hope I haven't fallen down on the easy bit. So what that tells us is two things. First of all, this is not a factor of this. Well, it's not a factor that will leave us without a remainder. And if we were to divide this by this, our remainder would be 9. That's useful because it saves time. Now, let's have a look at factor theorem. Now, factor theorem, just to restate what factor theorem said, it said that if PA equals 0, then x minus a is a factor of px. What does that mean? That means if we take this and just write out x plus 1, which means that if this is to be made 0, x must equal negative 1. So the link between these two is that if you write this, this format will be negative 1. Okay? So what factor theorem tells us is that if we put negative 1 into this expression, and for our trouble we get 0, this is one of the factors of this expression. That's really useful because that avoids a long division. Okay, let's get to work. So negative 1 cubed plus 6 times negative 1 squared minus 11 plus 6. That's what this all works out to, which gives us negative 1 plus 6 minus 11 plus 6. Negative 11, negative 1, that's negative 12, plus 6 gives us 0. This thing is a factor of that because the remainder was 0. Now, here's the evidence. Okay, so because I don't want you to, I went to the trouble of doing the long division of this. And I divided x cubed plus 6x squared plus 11x plus 6 by x plus 1. And I'll just talk through the working very quickly. Multiplied that by x squared to get this. Did the subtraction. 6x squared minus x squared gave me 5x squared. Bring down the 11x. Multiply through by 5x and I get 5x squared plus 5x, subtract that, and I get 11x minus 5x, which gives me 6x. Bring down the 6. How do I get this from this? I multiply by 6, so I get 6x plus 6. Subtract that, and I get 0. So this divided by this leaves a remainder of 0 and tells me that this is a factor of this thing without a remainder. So just to go back to this quickly, I did the same thing using factor theorem here, and I got a remainder of 0 which told me that that was a factor. Okay, what am I left with? Well, I'm left with a quadratic up here, and that's an easily solved quadratic. So basically what I'm able to do by this this sort of process is, first of all, confirm that this is a factor. And if that's all I have to do, well, that's fine. But if I have confirmed that this is a factor, then what I can do is I can do the long division and discover the other factors potentially. And in so doing, I've discovered that x squared plus 5x plus 6 is another factor. And when I factorize that, which I have done here, it's nice and simple to factorize, I get x plus 2 and x plus 3. Now, going a little bit beyond remainder theorem and factor theorem, the fact that I've got 1, 2, 3 factors of this cubic means that I am able to discover where, when I graph this, the x-intercepts of this cubic would be. We'll get into that in another video when I get into graphing cubics. Anyway, we have the two other linear factors here. So what I decided I'd do is I'd take this x plus 2 and see if it worked using factor theorem. And here we go. So the factor is that, so that's the number that I put into this. So negative 2 to the power of 3, negative 8. 6 times negative 2 to the power of 2, 24. 11 times negative 2, negative 22, negative 22. Plus 6. Okay, here goes. So 24 and 6 is 30, minus 22 minus 8 gives me 0. Yes, confirmation as if I needed it, that is a factor of x cubed plus 6x squared plus 11x plus 6. Now, on a good day, you might get a cubic that looks like this, and you might just try putting 1 into it, negative 1 into it. You might get lucky with, say, negative 1 as we did here. It wasn't all luck. I actually created this so that it would work. But if we put negative 1 into this, we discover a factor. And that might encourage you to try 2 or negative 2. And you discover with negative 2 that you've got a remainder of 0. That might further encourage you to try 3 or negative 3. And if you try negative 3, you will get 0. So it is possible, although it is a diminishing return, it is possible by trial and error to use factor theorem to find all of the factors of a cubic, if the cubic is cooperative. If it's one that's got remainders, well, that's another story. The textbooks that I see, they tend to have questions, find a factor of x cubed, whatever. They tend to have questions that require you to use 1, negative 1, 2, negative 2, 3, negative 3. And I used to tell my students, after 3 and negative 3, give up and do a long division. But I have seen questions where you're asked to use factor theorem to crack a cubic, and you've had to go up to 5. Which is getting pretty awkward because, 5 cubed is 125, and if there's a coefficient in front of that, it's an even bigger number. But I am starting to see questions like that, so just be prepared. But the basics of remainder theorem and factor theorem are this. Remainder theorem allows you to quickly work out what the remainder will be if you divide a polynomial by a factor. It doesn't have to be a linear factor, but a linear factor is more ideal. It's a shortcut. You can confirm it with long division. Factor theorem may be a result in itself. It may just allow you to find the genuine factors of a quadratic or a cubic or a quartic or whatever, although why you'd go to the bother with a quadratic I don't know, but theoretically it's possible. Okay, well, I hope that cleared up a few things. Thank you very much for watching. See you next time. Bye.